Hi, my name is Joseph Rabinovitz, and this video is for Stewart's Calculus, Chapter 1. So the beginning of the chapter reviews a lot of elementary functions, and if you need some refreshers on that, please look at our pre-calculus video. I'm going to start here with two of the problems that kind of inspired the need for calculus. And the first problem is probably one that you're a little bit familiar with, the tangent problem, because you've dealt with tangents before, namely lines that lie tangent to circles. For example, just to give you a refresher, here we got a circle, and the tangent line is one that just passes through one point of the circle. Now in calculus, we're going to be dealing with lines that lie tangent to functions, and I'm going to give a more refined definitions for this later, the book does later on, but basically for now you can think of it very similarly. So here we've got a parabola, and the tangent line is one that just passes through one point, like so. Now, one problem that Newton had and Leibniz had when they invented calculus was, how do we find this line? How do we find that slope? And how do we find the equation of that line? Well, that's what calculus does. And one thing that people thought they could do before was something like this, some very precise averaging. Here, I'll show you a little video of this. So, we got a parabola here, and here's the tangent line. I'm not going to go through how to find this tangent line quite yet, because we'll get to that in a couple videos, but just know that it passes through only one point on the parabola, y equals x squared, and it looks like this. The equation is y equals 2x minus 1. But how did we get there? Well, you may think, let's see what the equation of the line is passing through 2 points on the parabola, like this, namely through points x equals 2 and x equals 1 to try to figure out the tangent line at x equals 1. And the slope here is 3. That's pretty close to the slope of the tangent line, but I think we can do better. Let's see what happens when we pass through points x equals 1/2 and x equals 1. Well, look at, you see that line's looking a little bit closer to the tangent line here, and the slope is getting closer. It's now 2/2. Pretty good. We can still maybe even do better. Ooh, there you go. This is the line that passes through x equals 1 and x equals 5/4 on intersecting the parabola y equals x squared. And now this slope is very close. This is 9/4. That's very close to 2. And so what you might be seeing here, let me get you one of the earlier ones. Let me unselect that. As this distance on the x-axis, let's call it d. So right there, d. That distance, as we start getting points on the parabola where that d gets smaller, then the slope, or the tangent line, becomes more precise at x equals 1. So we can say, as d approaches 0, we'll find the tangent line at any point x on a curve. It's pretty neat. This notation here, if that seems weird and kind of frightening to you, don't worry. The next chapter we're going to be covering limits, and limits deal with stuff that approach things. Very vague, but there you have it. And so so here we go. The next problem is the velocity problem. So the problem basically goes as such. We can calculate average velocity. Or let me actually go back here. We can calculate average velocity, and average velocity is called VAVG equals a change in some distance, and I'm going to call that distance x, over some change in time. So that means if an object travels some distance in some given amount of time, we can calculate the average velocity that it takes to get there. But what if we want to calculate a precise velocity of only one point t? In other words, that's called instantaneous velocity. Here, I'll write it down over here. Well, that seems kind of weird. How can an object have a velocity for just 1 point time? That would mean that this t would be approaching 0. That's kind of funny. So let me show you a good kind of numerical analysis to organize this problem. So we've got change in t. So that means, oh, let me tell you what this function is. This function that I'm going to be dealing with is actually Galileo's function for a falling object, which is s, which is also x. Same thing. Equals 4.9t squared. That's nice. It's a parabola, so we've been dealing with that before. And so say we want to figure out what the velocity of an object falling is at exactly time equals 3. So at 3 seconds. So what we can do is, oh, where'd it go? There it is say, all right, so we're going to calculate the average velocity of this object between 3 and 4 seconds. Hence, the change of t is 1. And then I kept using Excel. I got a function that told me what the change of x in that time is between 3 and 4, and then the average velocity right here. Well, let me put in 0.95 and then expand this out so that this change keeps getting smaller and smaller all the way until we get to 0.05. And let's see how the average velocity changes. The average velocity gets down to 29.645. And this may just seem like, oh, it's a decreasing function and it'll decrease forever. Well, let's see about that. So we put in 0.04, make my step smaller, my increment smaller, and go down to 0.01, and then let's see how this guy's changing. Okay, so now we see that it kind of stays close to 29 and seems to go to about 29.5. So that's kind of interesting. As the change of t, let me go back over to my sketchbook here. I'm going to erase all this. So as our change of t gets smaller, then the instantaneous velocity, we seem to get some sort of instantaneous velocity. So as change of t, this might look familiar, approaches 0, our instantaneous velocity starts to appear. And so now we see that this problem is very similar to our earlier problem with the parabola, with the tangent problem. It's all about getting little tiny increments to get even the tiniest that they can be in order to find some sort of slope or velocity. And we'll see later that that slope and velocity end up being the same thing. Stay tuned for our next video. Our next video is going to be on limits, and I might clear up some of that funky notation for you.